Hello class, welcome to the next segment in lecture 27, and in this segment we're going to talk a bit about how our formulation for lapse rate changes when we go from Cartesian coordinates to pressure coordinates. So with that, let's go ahead and dive right into it. So just to refresh your memory on the standard Cartesian formulation for lapse rate. The standard Cartesian formulation for lapse rate goes something like follows, where lapse rate is represented by uppercase Greek letter gamma. That's defined as the negative times the how temperature varies in the vertical direction. So by using this formulation, lapse rate values are typically reported as positive values, even though the temperature is decreasing as you go up in the atmosphere. So let's say the temperature decreases at a rate of 8 degrees C per kilometer. That would represent that lapse rate would be reported as positive 8 degrees C per kilometer, but this term dTdz, just the value of this actual term, would in fact be negative 8 degrees C per kilometer. As you go up, every kilometer you go up, temperature decreases by 8 degrees Celsius. So by putting this negative value out in front here, this causes lapse rates, that is the rate at which the temperature falls, to be reported as positive values. So let's take a look at how this formulation changes when we go from Cartesian coordinates to pressure coordinates. So we're going to do the same trick that we did in the previous segment with the mass continuity equation. So we're going to again invoke a form of the chain rule, something that we hopefully remember from calculus classes. We can invoke a form of the chain rule. So again, I'm going to do the same trick that we did in the previous segment on the mass continuity equation, where I'm going to split the numerator and denominator into two separate fractions here, so that I have the old numerator dt with an empty denominator, and I have the old denominator dz with an empty numerator. And just like before, we want to put the same differential in for these empty spaces in our fractions here. And again, since we're interested in how pressure changes with height, or how the temperature changes with pressure, instead of centered height z, that's the essence of going from Cartesian to pressure coordinates, it would then make sense to put dp in for this denominator, and also to maintain balance, to make sure we don't change anything, we also have to put dp in this numerator. Excuse me. So we get basically we get this formulation where we have dt minus dt dp times dp dz. And again, if you look at this from the same algebraic standpoint that we looked at in the previous segment, you can see how these differentials dp would in fact cancel out if we so desired. So we haven't really changed anything in our equation. So we also so just like before, we also have to recall that dP/dz is in fact equal to a very specific quantity in the atmosphere. This is in fact the hydrostatic formulation. So we get that dP/dz is equal to minus rho g. And just like before, we can take this expression for dP/dz equals minus rho g, and simply take that expression and plug it in for dP/dz. And if we plug that value in and cancel out the negative signs, then we get that in pressure coordinates, the lapse rate is equal to density rho times acceleration due to gravity g times how temperature varies with pressure. So just like what we did in segment 2, when we looked at how the vertical velocity changes when you go from Cartesian coordinates with w to pressure coordinates with omega, let's take a look at and see how these values change, how these values are related when we take a look at, say, an example profile of temperature. So let's take a look at, first let's take a look at the standard Cartesian formulation, so that we get sort of a baseline of what's going on here. And the units for the standard Cartesian lapse rate are, of course, we have temperature in the numerator and some sort of distance in the denominator. So the lapse rate is going to be kelvins per meter, or what's more often used in operational meteorology, kelvins per kilometer. So dT/dz, just this quantity, is going to be in units of kelvins per meter and kelvins per kilometer. And I also want to go ahead and say that the graphs that we're going to look at, we're only going to be looking at the values of the derivatives. So in the Cartesian coordinates, we're going to be looking at whether dT/dz, just this quantity without the negative sign, we're going to be looking at if that is positive or negative. And when we go to look at pressure coordinates, we're going to be focusing on dT/dP. We're not going to be worrying about the factors of rho and g out in front of it. We're only going to be focusing on the derivatives and not the terms or the values that appear out in front of it. So we're only going to be focusing on dT/dz here, just this derivative without the negative sign out in front of it. So let's take a look at again, we'll take a look at some sort of axes to sort of get our bearings. And let's go ahead and plot, say, a theoretical value of temperature. So this red line here represents temperature, and as you go towards the left, you go towards lower values of temperature, and as you go towards the right, you're going towards higher values of temperature. So you can see in this particular case, as we go upward in the positive z direction, as we go upward in the vertical direction, our temperature is decreasing as we go upward. So that means that our value in the numerator here, dt, is negative, and our value in the denominator, dz, is positive. So this entire quantity, dt dz, is in fact negative, since my temperature is decreasing as z increases. And you can also look at this in the reverse. So you can look at how temperature varies as you go in the negative z direction. So as you go in the negative z direction, temperature increases, which also gives you a negative value for dt dz. And so since dt dz is negative, then we say that, of course, the temperature decreases with height. Now let's take a look at how things change when we go into pressure coordinates. So pressure coordinates, the formulation that we derived earlier, is that the lapse rate gamma is equal to rho g times dt dp. And if you take a look at just this differential here, just this derivative dt dp, you see that we have temperature in the numerator and pressure in the denominator. So over here, where we had temperature in the numerator and height in the denominator, our units were kelvins per meter or kelvins per kilometer. But since we have temperature in the numerator and pressure in the denominator, then we would have units of just this term. The units for that would be kelvins per pascal or kelvins per kilopascal. So that's one difference to note, is that, again, we're just focusing on these derivatives here. So just focusing on dt dz, and here we're just focusing on dt dp. Just dt dp has units of kelvins per pascal or kelvins per kilopascal or even degrees Celsius per some unit of pressure. So let's take a look at the same exact temperature line, but let's take a look at it in the pressure coordinate system. So again, the pressure coordinate system has higher values of pressure being directed downward and lower values of pressure as you go higher into the atmosphere. So let's take a look at the same exact temperature line that we have over here. Same exact temperature line. And as we go upward, as we go higher in elevation, we're going towards lower values of pressure, but we're also going towards lower values of temperature. So temperature decreases as pressure decreases, which means we have a negative value in the numerator and a negative value in the denominator, and those two negative signs do in fact cancel out. So since, again, temperature increases as temperature decreases as pressure increases, that would then tell us that our quantity dt dp must in fact be positive. So just like with the formulation for vertical velocity, when we go from Cartesian to pressure coordinates, we sort of pick up a negative sign there, where w is positive, omega is negative. In the case of vertical velocity, in Cartesian coordinates, if dt dz is negative, then in pressure coordinates, that would mean that dt dp is in fact positive. Now let's take a look at a different example. So let's take a look at an example where instead of instead of temperature decreasing with height, let's take a look at where temperature would be increasing with height. And this would be, say, like an inversion somewhere in the atmosphere. So let's take a look at, again, the same exact temperature traces. But here, these are going to, of course, this is going to be a temperature trace where temperature increases as we go upward. So again, let's take a look at what the value of this derivative dt dz is. So this time, as I go upward, as I go towards lower values of z, as my z increases, I'm going towards higher values of temperature, which means I have a positive value for dt and a positive value for dz. Hence, dt dz, that quantity must be positive, which implies that, again, we have a temperature that's increasing with height. Now let's take a look at dt dp. As we go towards, so again, as we go up in the atmosphere, we're going towards lower values of pressure, so dp is negative. And in this case, as we're going to higher elevations where pressure is lower, as we're doing that, our temperature is in fact increasing. So as pressure decreases, temperature increases. So that means that I have dt being positive and dp being negative, which means that entire quantity, dt dp, is in fact negative. So just like with the vertical velocity in Cartesian versus pressure coordinates, if w is positive, In Cartesian coordinates, omega in pressure coordinates must be negative. And if W is negative, omega is positive. And the same convention holds when you take a look at the derivatives here, dt dz versus dt dp. In the case of Cartesian coordinates, if dt dz is positive, then dt dp is negative. As we saw earlier, if dt dz is negative, then dt dp is in fact positive. So that's going to do it for this segment on how lapse rate changes when we go from Cartesian coordinates to pressure coordinates. And in the next segment, we're going to take a look at how you can where to find the value of omega on a sounding. And in fact, you can only find it on a forecast sounding, but we'll explain why that is the case in the next segment, which is also the final segment. So with that, I will see you all there.